Hello everyone, today I'm going to explain you about the ingestion part of this application, which is very integral part of this application because it's about how we are ingesting the normal content of the file into the vector dimension in the vector storage. So let's just start with it. So we have these components, we have our application here, we have S3 bucket here, we have our database here, we have our vector storage which is Universe, and lots of things. So I have to keep very large. Whenever a client request, they would provide a file IDs they wanted to ingest. So that's the metadata they are going to provide. Reference, I would say they would provide file IDs. The application has a logic handler which would then fetch object keys, and then it would publish it to a queue which is SQS queue, Amazon based SQS queue, because we wanted something robust which could persist the information. At the same time we wanted something simpler and we wanted something cheap, and SQS free tier is like you could publish 1 million messages, so that's enough for the small scale, 1 million messages. So we published to an SQS queue, and the part here is that we are going to again consume from that same SQS queue within that application. Of course, that's it's a VR practice, when you would say, to a processor manager. It's just a part of same application, but the reason to do and to decouple it to a remote queue, not the queue within you know local application, because we wanted to persist it remotely somewhere, so it could be processed again, and we don't wanted to make another dependency in the application and make it more complex, because it's already a complex application. That's why we thought that managing queue would make a little bit simplicity, and it would make it won't overwhelm the application if we implement queue logic inside. So I thought it would be good design, and we have to also consider the trade-off of money and the cheapness of it, because we are building something more cheaper and more better alternative to managing search. So that's why we have used SQS queue, and we are polling to the same SQS queue within that same application. And the processor manager, what it would do, it would receive those object keys and file IDs, all that metadata information, and it would fetch that temporary the object from S3 and download it temporarily. And those are sets of file IDs, not just a single file ID. It could provide multiple set of file IDs to ingest, and that could happen, and those would be handled concurrently using a sync IO. So it's a concurrent system, it's a fast application we are building, so it can handle the scale also and the speed and with a lesser latency. So once we receive that object, we download it temporarily inside our application. What we do then is somewhere very important. We process that file. So basically we are processing through, we have used LangChain library. LangChain has wrapped around the unstructured library. So under the hood, under the base, the library which has been used is unstructured, but to make it more better and usable across the application, we have used LangChain as a component to use unstructured, because it wrapped into document object. Let me show you the code. What I mean by that is, when we are processing a file, okay, these are the loaders for different we have created a loader factory which would load those documents. See, that's what I'm talking about. The LangChain, we have used document loader of LangChain library to load those kind of document, and we could handle multiple types of documents. But the bigger part is we are processing that document. How we are processing it is basically we are first downloading it. So here's the code. See, process file. So basically downloading the file. Once we download that file from S3, we are creating a loader based on the file type of it from the extension, and when we load it, so based on that extension we have a loader factory. It would have a structure, a structure manner that could describe LangChain that this is the file extension, and this is the way use this thing to parse it. So LangChain has multiple parser, so it makes it easy to manage this. We can't build in the solution for that, because then we have to have a object for managing those documents. At the same time we have to manage those parsing also. So everything has been wrapped around in one single thing via LangChain, via this loader factory. So basically you load the document, mentioning it would parse it, the file extension. Based on it would parse the file and generate a document object, which would be easy for doing other operations. Okay, next thing we do is semantic chunking, but it's not actually semantic chunking, it's a mixture of that, and we are using parent document retriever. This concept is very fascinating. It's not, see, earlier I implemented a semantic chunking, but what was the issue was that when you do semantic chunking, you consider a buffer of one or two sentences. So if you have one sentence for semantic chunking, you would consider two sentences before that, and you would consider two sentences after that, maybe four sentences. But that would be stored into vector storage. So whenever searching would occur, it would fetch those four sentences. It won't fetch the larger context of whole. So it would be harder for LLMs to generate the whole contextual response, because only those four sentences, and based on that LLMs would generate response. So when application wants to generate a larger contextual response to the user prompt, and based on searching, we are going to use parent document retriever. It's a robust mechanism, and using the Greg Kamrath guidance, he has shared about the parent document idea, and there wasn't a single library which implement a parent document retriever. So what I thought was, combining the semantic chunking and my own logic for parent document retriever, why don't I create my custom class for parent document retriever? And this is what I did. And this is the custom class, and this is the best part which I designed about, and this is what I like about this application, and this is the best part I feel that I've created here, which is again a wrapper on top of other things. It's not just my thing. It has been built upon LangChain, it has been built upon other libraries, but it's a good thing that it has been built. Now, how we build a parent document retriever, let me explain to you. So first we are doing sentence parsing. See, we are doing a sentence splitting. The sentence splitting is done using Spacey library. We are giving a Spacey command to just parse. We don't want it to do it just based on regular expression. We wanted something more specific and more accurate. So that's why we are using this Spacey model. It is very lightweight model to split a sentence accurately. So that's why we are using that, because our utmost priority is accuracy, and that's why we are using sentence splitter, and we'll split those sentences, and the larger documents will be splitted down into sentences. Let me see when we use sentence splitter. Okay, so whenever split text is being called, so initially the transform documents has been called. This is the function which we import, and we execute this transform function, but these are all internal public methods which are only used by internal class. And so you split a document. The first thing is you create a parent chunk docs. How parent document retriever works, let me explain it to you. So you have a large document. And so you semantically split. We are not splitting just with the paragraph or hierarchical manner that 10 sentences split, 10 sentences split. We are splitting semantically larger chunks. And how we are semantically creating a larger chunks, that's the greatest part. So we are first doing sentence splitting, and after sentence splitting what we are going to do, we are going to do buffer based semantic chunking. So what we are doing is we are saying that consider 5 sentences, we are targeting one sentence, and we are saying consider 4 sentences above that and consider 4 sentences below that. So there are total like 8 sentences, and you are trying to build a semantic embeddings based on that, and then you are trying to combine it all. So this would lead to a parent larger chunk. So basically you would have 15 sentences, maybe based on buffer size, and maybe based on semantic chunking you would have 15 or 20. So that would eventually lead to a paragraph. So better a larger chunk, and those larger chunks would then be stored in the database. It won't be stored in vector storage. If we store the larger chunks in the database, in the vector storage, my bad. If we store the larger chunks in the vector storage, that is going to consume lots and lots of memory. It's going to consume lots and lots of database storage, and we won't do that. What we would do, we would store the parent chunks in the database, but we would store the semantic, the sentence based small semantic chunking into vector storage collection, and we store that into vector storage, let me copy it. So basically this is the semantic chunking of that, this is the semantic chunking of this, and this is the semantic chunking of this. But how they refer it to it, they have a parent ID. See, let me show you the schema. That we have a parent ID. See, this is the field which we add, and that navigates back to the database. So this is referring the parent chunks in the database, and so this semantic chunk, the smaller chunks it would have in that collection, would navigating back to parent ID. So when you are searching in the semantic chunking, but it's pointing to parent chunk. So when you found that you have a list of search results, those are all pointing back to parent chunks, and you will bring back that parent chunks. So what will happen, you have a total different ranked results, like top 5 results. You would have a larger context to those each individual corresponding results, and then think how better the LLMs could generate a better response, and that's how it impacts the whole system. So this is how we are doing parent chunking. And so once the parent chunk is done, we do semantic chunking of each parent chunk. You can see that we are creating a document based on parent chunking, and then we are looping through the parent chunking for calculating semantic chunk of each parent chunk. We are creating a generalized document object, so it's better to for other operation. You can see this is the document object. So create documents itself is operation which we do to create. It's a common method for semantic chunking and for parent chunking. And so let me show you the split text. It is very important. So basically you split text using sentence splitter, that is a spacey model to split a sentence. Then what you do, you calculate the sentence distances. Okay, after calculating the sentence distances, this is very important. The way we are calculating sentence distance is through we are combining a buffer. See, if it's a parent chunk, if we are splitting text based on parent chunking, we would say we need a buffer size 5, which if you are targeting that sentence, you are targeting 5 sentences before that, we are targeting 5 sentences after that. So total 10 sentences we are targeting. No, my bad. We are targeting total 11 sentences. counting that sentence which we are talking. And then we are calculating the semantic chunk. So this would have a larger context, when we are calculating it. At the same time, we are looping through all the sentences to find a semantic meaning in between those, and that would create a marvelous parent chunks. And then you would loop over those parent chunks and create semantic chunkings for everybody. So this is how parent document retriever we are working, and let me show you the demo how we are actually doing in the application. So first let me upload a document. I've created a knowledge base in the earlier video. This is the one. Now let me upload it. One thing is that I need to run a S3 application to upload a file, because it's a custom application I have written, because I wanted to upload programmatically the file to S3 directly by pre-signed URLs. That's why. You can do whatever you like. I'm running this, and I would directly upload it to pre-signed URLs using this. Okay, it has started. Now let me create a document first. We need to upload it. Simple reference. I got this pre-signed URL, which is of type PDF because it's a PDF. That's what I am uploading. So this is this tooling. This tooling, which is not part of our code, which is not a part of our project. This is my custom tooling which I'm going to upload to, for which is easier for me to upload to S3 rather than manual work. So this is the file, and let me upload it. So it got uploaded, it's successful. Now I will finalize the upload document, because we know the ID was 1 and was successful. Then we are going to do it successful. Okay, and when we list it, see, the file has been successfully uploaded and it shows the entry to that. And if we actually in the database, there is an object key to that. Okay, and so that's the part of it. And this is a report operation, so sometimes we need to clean up. So there is no explicit, we have given explicit API endpoint to clean up those documents, because sometimes you would generate a pre-signed URLs, but there would be failures to upload. So there would be half database record, inconsistent database record, which would be in pending state. And so to clean that up, we are going to run a reconciliation process in the application that has been running about the cleanup, but you can explicitly trigger also. That's the thing. And when you audit the code, you would get those kind of things. Let's just start with the ingestion process first. We have those knowledge base right now. Okay, we wanted to ingest data, and how we are going to do that. So basically, our knowledge base ID is 1, and the file ID is 1, and we're going to ingest it. Okay, so the job has been started, but it's pending. It has not, see, has been processed from the logs. It is, see, it receives a message from SQS. It's going to process it. See, this is all, everything. This is the request we send it to OpenAI to calculate the embeddings, and it calculates the embeddings, and it's and of course there's like lots and lots of logs, but it's for showing you that this is happening under the hood. And if you see, we can hold the job status also. So it should show pending status. It's processing. Okay. Okay, it's processing. This is what large document, so that's why it's taking some time. Of course, size was smaller, but there were like lots of textual content. So it's taking some time to say to process it. So let it process it. It's taking lots of time. Let it take it because it's processing it. Okay, okay. It's taking some time, but you could see that the job status is pending. You get this. And initially it showed buffering because see that's the limitation of this application because it's a couple architecture. You are processing the file within that application at the same time you are hosting the API endpoint. So that's going to limit this whole idea of it. You are going to face some time latency based on that. That's fine. And you can see it has finally completed. It was really large ingestion process because there were like lots of textual content, but you can see it has been processed. You can see it is now been successful. See, successful. So this was all about the ingestion process, and let's do searching and see how the searching works, and let's see what document the knowledge base has because we are also creating a record here. See, this is now ingested, that's why it's showing that it has a record. So another way of polling the job about the ingestion is that you could check it that is there a document that has been created into the knowledge base. If it's not been created, that means it's not been ingested. So that's one thing, but at the same time you could poll it for the ingestion job status. That's also one thing. It was a long process. I just paused it earlier because I was kind of confused and scared that something fall apart, but it wasn't. It was a long running process because it was a research paper. Let me show you the whole document which I have uploaded, which is this thing. Yeah, this is like lots of content. It's a 19 pages. So let's do searching through it, and let's do searching. Searching is going to take some time because it's a large document. At the same time, we are doing synchronous searching. We are not creating a job and searching in the background. No, we are doing it synchronously. So let's take anything from the sample PDF. Let's retrieve performance. Searching, it has been doing searching. Oh, that's really fast. That's really fast, man. That's really fast. Oh, that's good. I didn't think that it would be so much fast, but yeah, we got it. Principal one could opt. Let's see. Principal one could opt. This is the part of it where it receives, and it's the closer thing. You could see this part is somewhere closer to this part. You can see in principle one could opt for a higher question on newer version but very strict, and we focus on possible across different data set. Okay. You can see that we have been in the result near to this part. Because we search about this and we got this. And when LLMs see this data, and if we just pass the two ranked research, search content, LLMs would be easily could generate response based on that. So basically, it's really good. So you can see that ingestion was a long running process. It was tedious process, but it's all worth it because search is really fast. You could see how fast it was. It was within 1 second. I guess it's really fast, and I'm impressed. I myself wasn't expecting that much speed, but it's good because it's millions. But yeah, that was it.